I try to focus on my pre-books and my form a lot. And I go slowly losing and then I go.
I know a few that are words. All right. Let's see. Let's start off with any questions you have. We'll be plugging away for a couple of weeks here at different types of random variables. The quiz, I have a quiz up here for you, the take-home quiz. I just figured it's a better use of class time to not have a quiz. So, and I can ask you slightly more interesting questions on a take-home quiz. So, any questions? Yep.
Number 13.
From
The book.
From the book, and 2.12. In chapter 2, number 15. Let's see, what was this? Okay. Two teams, A and B, play a series of games. If team A has a probability of 0.4 of winning each game, is it an advantage to play the best of 3 out of 5 or the best 4 out of 7? Assume the outcomes of successive games are independent. Right? So we have these two. Right? So the probability that A wins is 0.4, right? And then the probability B wins is 0.6. And so then they start playing, let's just say, the best of 5. Right? And so then the question would be, what is the probability A wins the series? Right? Which would mean A would win 3 before B wins 3. Okay. And we're going to assume games independence, which, is that a good assumption? In most streaks, things get pretty streaky. So you can see, right, we have to make this assumption, because if we don't make this assumption, we have to make some other assumption, like, and we could do this. If A wins the game, then the probability of A winning the next game is, let's say, 0.5 or so. I mean, you could adjust it in that way, but then you're making it more complicated. If we just want a really simple, sort of stripped down game, then we're going to assume independence. But that assumes no streakiness, that if you win a game that you're likely to go on a roll or things like that, which oftentimes does happen in sports. Okay. So, A wins the series. I guess one of the questions would be, how could A win the series? Okay. There's 3 ways, well, we could break it down this way. A wins in 3 games, right? Or
A wins in 4 games.
yeah. A wins in 4 games. And maybe I should use the word exactly. 3 games, exactly, just to make sure we understand those are different things. You either win in 3, if you win in 4, that's not the same as winning in 3. Or A wins in exactly 5 games. So let's see, if A is going to win the series, this is how A is going to win. Okay. And now the question is, what's the probability A wins the series in 3 games? In exactly 3 games. There's these 5 games here. What happens for these first 3 games? A. And what's the probability of A winning? 0.4, and a 0.4, and a 0.4, and I don't even have to play those games, right? That's just, it's already done now, A won. And so the probability A wins in exactly 3 games should be 0.4 cubed. Right? Not incredibly likely, right? 0.4 times 0.4, that's 0.16 times another 0.4, what is that, 0.07, maybe 7% of the time, something like that, maybe 6. Okay, but that's how A wins. How does A win in exactly 4 games? How does this happen? Well, now we need to put another game in here. How does A win in 4 games? What has to happen in the 4th game? A has to win that last game. What has to happen in the first 3 games? You choose to. Yeah, B's going to win 1 and A's going to win the other 2, right? It could be B, A, right? But they're actually going to be 3, and I could choose 1, or 3 choose 2. This same value, they're both 3, right? I could pick 2 of the first 3 games for A to win, or I could pick 1 of the first 3 games for B to win. It gives me the same thing. And then B winning is a 0.6 and a 0.4 for A, and then a 0.4 for A. Yeah, so how does A win in exactly 3 games? 3 choose 2, right? There's 3. The first 3 games choose 2 for A to win, and then A wins 3 of them, and then B wins, B, 0.6 wins the remaining game. Or I could put 0.4 squared, 0.6 to the 1, and then another 0.4. Just if I really wanted to emphasize that, A has to win the last game. Okay. 5 games. What happens? A wins the last game, or it never went, right? It never went to 5 games. So A has to win the last game. And then of the first 4, B must win 2 and A must win 2. Seems like a 0.6, 0.6, 0.4, 0.4, 0.4. But then how many different ways can I choose those? Either 2 for A or 2 for B wins. I have my 4 games, and I'm just going to choose 2 of them for A or 2 of them for B, however I want to think about that. And so I would get something like, let's see, 4 choose 2, 0.4 cubed, 0.6 squared. And if I want to think about it now, I could have thought about this as 2 choose 2. I had my 2 games, I had my first 2 games, but A won both of them, right? 2 choose 2, 0.4 cubed, and 0.6 to the 0 if I wanted, for sake of completeness there. But that's what would end up happening. And so if I add all those up, it'll give me some probability. Okay, that's best of 5. Can we figure out best of 7 then? I don't necessarily want to finish this off, but what would differ if we did a best of 7 instead of a best of 5? What's that?
Winning at 4.
Yeah, 4. So A could win in 4 games, in 5 games, in 6 games, or in 7 games. Right? And then what's the probability of winning in 4? 0.4 to the 4th power, it seems, right? What's the probability of winning in 5? Let's see, if it's all going to be consistent. Of the first 4 games, we're going to choose 1 or 3, depending on who we're looking. We'll choose 3 for A to win, which means B won 1. So then it would be something like 4 choose 1 times 0.4 to the 4, and then 0.6 to the 1, right? And we could go through the exact same argument in a best of 7. 4 choose 3 now to be the 0.4 to the 4th, and then 0.6 to the 1. Or we could have the, let's see, if it goes 6 games, then I need to choose out of the first 5 games, 3 for A to win, which means there's going to be a 0.4, again to the 4, and 0.6 squared plus, we're almost there. 6 choose 3. Of the first 6 games, choose 3 of them for A to win, 0.4 to the 4, means that B won 3 games, 0.63, right? That's the probability of A winning in 7 games. Okay, and if I want to know what's the probability A wins the series in 7 games, this time I would add those numbers up. And it would give me a probability A would win the series. And then I could compare this number here to that number there, and whichever one's larger would be the better outcome, right? The more likely that A would win that particular series. typically the longer you go, the more this sort of goes along with what's called the law of large numbers. If you repeat something often enough, what you expect to happen will happen. Well, if you repeat, these games often enough, you expect the better team to win. So longer series should indicate that B is more likely to win here than up here, which would then mean A should be more likely to win here than here. Right? Just like if you just play one game, A has a 40% chance of winning and B has a 60% chance of winning. A is probably never going to do better than that. Every time you play another game, it's just another chance to lose. For the losing team. Okay? All right. Now this isn't exactly one of our random variables that we deal with, but it is sort of tied in with the way that we think about each game is a Bernoulli trial, right? Each game is a Bernoulli trial with a probability of success equal to 0.4, and a probability of failure from this context, right, with A's winning is a success, 0.6. And then independence means that I will multiply, but it's certainly not a binomial random variable. It looks a little bit like something like a negative binomial random variable, which we might talk about by the end of class, but probably we'll talk about on Monday. Okay, but this idea of figuring out what could happen, how many ways could it happen, and independence allows us to compute probabilities by just multiplying things together. Okay. There you go, there's a random variable. Let's go back. I want to finish off binomial and start geometric today. Actually, probably finish off geometric if we can today. So I left up from the last time some things about the random variables. We won't keep the running list forever because we'll have too many of them after a while. But a Bernoulli random variable has one parameter, we call it P. We have a probability mass function for that, is one way to write it. Okay. Expected value for a Bernoulli random variable we calculated last time was P. And the variance, which we sometimes call sigma squared, we calculated last time or time before even, Bernoulli random variable, and it was P times 1 minus P, right? The probability of success times the probability of a failure. Okay. And then the next one was the binomial random variable. So this was one Bernoulli trial, and K was 0 if there was no success, and 1 if there was one success. But now binomial random variable, we repeat our Bernoulli trials up here, right? This thing that has a probability P of success. But we repeat it a fixed number of times, right? N times. Okay. So a binomial random variable always has two parameters attached to it. Okay. An N and a P. And in a probability question, we assume we know what both of those things are. In a statistics question, we might know what N is, but we don't know what P is, and we would want to estimate it, for instance. But there's always two parameters attached to that, N and P. Okay. X is going to count the number of successes in these independent Bernoulli trials. Okay. And we wrote down the last time the probability mass function, right? Probably P equals K is N choose K, right? I have these N trials, I'm going to choose K of them for successes, and then I have P to the K corresponds to the successes, and 1 minus P to the N minus K corresponds to the rest of them being failures. Okay. So my probability mass function would be that term, or it would be 0. Right, for all the other K values. And last time we computed the mean, or the expected value of X, as N times P. And if you remember, we did that because we wrote down the binomial theorem. K equals 0 to N, N choose K, X to the K, and Y to the N minus K. Right? Which is what if I were to plug in P equal to, X equal to P, and Y equal to 1 minus P, I plug it into the right-hand side, I have these things for my probability mass function, okay? And if I sum all of them up, right, then I get, well, this is going to be X plus Y will be 1 to the N would equal 1, which says that if I add together everything in my probability mass function, it's just sum to 1. And that's exactly what we saw. Okay. And then for the expected value, we did this last time, of x, we want to sum k times n choose k, I guess p to the k, 1 minus p to the n minus k. Okay. And how did we end up getting a, because we don't have a formula for this off the top of our heads probably, not like the binomial theorem, which we should know, right? But so how did we find a formula for that? Well, how do we find formulas from any good series type problem? We manipulate it in such a way to get that, right? So we wanted, the difference was we wanted a k here, right? Otherwise everything else remains the same. And the way we could get a k out in front here is by differentiating with respect to x would bring a k down. So if I take the derivative with respect to x, I get a k down there. The problem is then I would end up with an x to the k minus 1. And how do I get an x back in there?
Multiply everything by x.
I can multiply everything by x. Okay? And that's what we did over here. That's what we did over here, right, on this formula, where we can start with our binomial random variable here, and if I differentiate each side with respect to x, I get this. The k came down in front, but I have my x to the k minus 1. But then if I multiply both sides of the equation by x, then I get this formula right here, which is exactly what I would want out of it. As long as then I go back and say, I have this formula that says something like n times x plus y to the n minus 1. And now I'll just do the same thing. I'll plug in x equal to p and y equal to 1 minus p. And then that's what I would have here. And what would it give me over here? A p, and then my x plus y would be a 1, and it would give me n times p. Right, that was the expected value calculation. And now, if we want variance, we'll want the second moment. Okay. And the second moment calculation will look an awful lot the same, except I'll want a k squared there, right, to go along with my piece of k, which would be my n choose k, p to the k, 1 minus p to the n minus k. And so then the question would be, how do I go back over here on what I call equation number 2, and how do I get a second k down in front? How do I get a first k down in front? The derivative, right? So I'll probably get my second k by taking a derivative, right? If I take the derivative with respect to x again, the k will come down in front, but then of course now my x is to the k minus 1, so what am I going to do about that? I'll multiply by an x, both sides by an x, and go through and get my new formula. Okay. So from equation 2, let me put this down here. Okay. Here's the formula I got that I used for my expected value calculation. Now if I take the derivative of each side of the equation with respect to x, then my k comes down in front and I get a k squared right there, right? But I'm sort of deficient in one of my x's that I'm going to want, right? I can take the derivative of the left-hand side with respect to x also. Not a Calc 1 class. I'll let you guys remember how to take the derivative of n times x times x plus y to the power of n minus 1, right? It's just a product rule with a chain rule attached to it, right? But if I take the derivative of the left-hand side, I get this guy. Okay? If I take the derivative of the right-hand side, I get this guy. And now if I want to get one x back in there, I can just multiply both sides of the equation by x, and that gives me a new formula. Right? That gives me my next formula. I'm being a little more careful with this on the binomial random variable, because we're going to repeat this a number of times. We're going to repeat it for a geometric series. We could repeat it for the Taylor series with an exponential, for an exponential function, right? That sometimes we want these new formulas, and how do I end up getting a k or a k squared out in front of something, or k cubed if I'm interested in a third moment, or k to the fourth if I'm interested in a fourth moment, right? Well, oftentimes it'll involve taking the derivative of something and then maybe multiplying by x again. So I have this formula up there. I don't think I'm going to write it down on the board. Okay. I have this formula up here that says okay, if I want to sum up, right, that second derivative of the binomial theorem with a couple of x's multiplied in at the appropriate times, then I get on the left-hand side something that looks like n times x plus y to the n minus 1 plus n times n minus 1 times x, I probably want it. So I get n times x plus y to the n minus 1 plus n times n minus 1 times x squared, is it? Yeah, x squared times x plus y to the n minus 2, right? And that's equal to this thing over here on the right-hand side, which is k squared and choose k, x to the k, y to the n minus k. Okay. Right. And so again, if I plug in x equal to p and y equal to 1 minus p, this is how we compute these expected values for general random variables, for general particular classes, then I get an n times p, x plus y would be 1, so that would just end up being 1. Okay. Plus n times n minus 1, p squared, and x plus y is just equal to 1, so that would end up being 1. And then this would be my calculation for my second element. Okay. And we remember the variance of x is the second moment minus the expected value of x squared. And that's the calculation we did last time. So I see something like n times p plus, let me multiply that out, plus n squared p squared minus np squared. And then I'll subtract off my expected value of x squared. My expected value of x was np. So that would be minus another n squared p squared. And I see plus n squared p squared minus n squared p squared. What's left? np minus np squared. I could factor out an n. I could factor out a p. And I'm left with 1 minus p. And that gave me my variance. Now the nice thing is once we have these formulas for expected value and variance, we don't have to go through and recalculate them every time. Right? If I know it's a binomial random variable, if I know n is equal to 15, and if I know p is equal to 1/3, then I know the expected value is going to be 5. I know the expected value is going to be 5, right, because it's going to be 15 times 1/3. That's my expected value. And I know my variance will be 15 times 1/3 times 2/3. Which will be, what, 10 thirds, right? 3.3 repeating. So I don't have to keep going through. That's the nice thing about having these formulas. But to develop these formulas, I typically would need to now go back and use, in this case, the binomial theorem, and manipulate it in such a way, take some derivatives, multiply by some x's, to make sure I get those proper terms out in front. Okay, right. But now we know it, right? These are the sorts of things. For Bernoulli, you should remember. For binomial, you should remember the mean, the expected value and the variance calculations here. I'll point out, for the important ones, you should remember these things. And again, I'm not one that generally wants students to memorize tons of things, but I mean, it's hard not to remember them once you've used them a half dozen times. All right, okay. Let's see, so we looked at the probability, so I think we've kind of taken care of everything with the binomial random variable there. So we're gonna go on to our next random variable in the next section, which is called a geometric random variable. So a geometric random variable is going to involve repeated independent Bernoulli trials again, just like the binomial random variable, except for we're going to count something different. We're just going to repeat it, and x is going to count the number of trials, the number of rounds, until the first success. Right. So I'm going to have to think of a coin flip. I'm going to flip a coin until heads appears. Okay. I'm going to roll a 6-sided die until a 6 appears. Okay. I'm going to pull light bulbs out of a box until I find one that doesn't work. Right? And the question is, how many times did I have to flip that coin, roll that die? How many light bulbs did I have to pull out and test before I found one that didn't work? Okay. Different than binomial, where I repeat something a fixed number of times and I ask for the number of successes. Here I'm just going to keep doing something until I have successes. Okay. So what sorts of values can x take? That's always the first question with a random variable. What are our values for a random variable? Number of trials. I could have a success with
Would it really be any integer?
any positive integer. Yeah. So 1, 2, 3, 4, 100, a million. I mean, it could be a billion, but I assume though it'd be a success unless it's a very unlikely thing to occur. But yeah, it really could be any counting number, any natural number, starting with 1 off to infinity. Okay. So here's my warning. I left this up from last class. Okay. So this book, and pretty much every book that I've ever come across, defines or thinks about the geometric random variable in this way, but it is not like a binomial random variable where nobody has a different idea about what to count. And so sometimes when people talk about geometric random variables, they're counting something different. Okay. And the book points this out also. Actually, I've not had used a textbook that's pointed this out before, but it's very timely, and I'll say why. So some people will say a geometric random variable is the number of failures until the first success. Right? Whereas our book and a lot of other books, they'll think of it as the number of trials until the first success. And what's the difference between those two things?
You have one less failure than you do trials.
Right. Well, you here you're not counting that one success, right? You're only counting the number of failures up until that first success. So those two things will always differ by 1, right? So whereas if my success is on the first time, then my x would be 1 over here. If my success is on my first time, then my x would be 0 over here. Right? If my success is on the second, then it would be a 2 over there. If my success is on the second, then it would be a 1 over here. Right? So we're counting the number of failures until that success. So everything gets shifted by 1. And I normally wouldn't point this out, or I wouldn't even worry about this, except when we're dealing with R, which we're going to be using R off and on through the semester, all these pointing out things, you'll notice I put +1 certain places because R does this, right? When R talks about a geometric random variable and does its calculations, it's counting the number of failures until the first success. And there's actually very good reasons for doing it that way instead of this way, if we want to tie it in with other random variables. But that said, this is the way that it is most often, and this is the way this book does, and so this is what we'll end up doing. Okay, so I just want to point out that not everyone calls a geometric random variable exactly the same thing. Okay, all right. So let's see. What can we do here? Let's see. Let's write down the probability mass function. It's always a good first place to start with a random variable. Okay. Probably, unless we see the big picture, how it's going to look. What's the probability x is equal to 1? What's the probability x equal to 2? What's the probability x equal to 3? Maybe we can see the pattern and we can figure out the probability x is equal to k. This is what we did with binomial. That's what we'll do oftentimes with these sorts of things. Okay. So what is the probability x is equal to 1? What's the probability I get a success on my first try? P. Because I have this success, right? It happens with probability P. At probability P, I'm done on the first flip. First light bulb was a failure, first coin flip was a head. How about when P is equal to 2, what happens? Well, it ends in a success, right? And what happened up to that point? Had to be a failure, which happens with probability 1 minus P. Independent Bernoulli trial says I multiply, right? Just remember, that's what independence means is, the first flip doesn't affect the second flip, vice versa, and I can compute a probability of failure first, success second by multiplying. So I'll end up with a 1 minus P times a P. Right. How about 3? What happened? I know it ends in a success. That's what it always ends in a success. So the first 2 were failures. So I had 2 failures, 1 minus P squared, and then I had my other success. Okay. No combinations, I don't have 3 positions, I'm choosing 1 because the last thing has to be the success. Because that's when I'm done, right? That's when I'm done counting. Okay. So what's the probability, X is equal to K? What's going to happen here?
1 minus P to K minus 1.
To K minus 1 and then a P. Yeah. Okay. 1 minus P to the K minus 1 and then a P. And that's going to be true for K equal 1, 2, right, on forever and ever and ever. If we're going to be very thorough about it, right, 0 for otherwise. Right? So, of course, this formula works when K is a positive integer, okay? Otherwise, I get the value 0. And again, the difference between this one here and that one there would be the difference between having this K minus 1 and just having a K right there, right? If the success is on the first try, then I had 0 failures in the success. So if you're dealing with the other version of the geometric random variable, wouldn't it be nice if we could just have a K there instead of a K minus 1? Anyway, but we have these K minus 1 there before on the last try we have our first trial. Okay. So that's our probability mass function. Probably worthwhile to point out why it's called a geometric random variable, because it's tied with a geometric series. Does anyone remember what the geometric series is? Should, because I gave you a handout on it. What's a geometric series? It tells us how to sum these things like 1 plus x squared plus x cubed plus, right? These things that look like the sum k equals 0 to infinity of x to the k. Right? How to sum those things, and what does it sum to? It's a handful of series from Calc 2 that you should, at some point, commit to memory. Definitely geometric series is one of them. It sums to 1 over 1 minus x. The other ones are the Taylor series for the exponential function, and if you're going to know those, the Taylor series for sine and cosine are always nice ones to know. Anything else? No, that's pretty much it. Binomial theorem, right, is that you should always remember binomial theorem. At some point, again, it comes up often enough. Okay. But if you want a sort of a refresher as to why this is true, if you multiply both sides of, if you multiply this term by 1 minus x, right, this series by 1 minus x, then you get a 1, and then you get a lot of cross terms that end up canceling out to some, like, x to the n plus 1 power, and be very careful here, as long as the absolute value of x is less than 1, as long as x is between negative 1 and 1, then those extra terms will go up to 0, and everything will sum to 1 over 1 minus x, right, for that sum. Okay. So let's be careful about that. And so, how does this help us, or how does this tie in with that? Well, think about it if I plug in 0 to infinity, 1 minus p to the k. Right? Because if I sum all these things up, I guess this is what it looks like. If I sum up all my probability mass functions there, little -1 there, and I guess we start 1 there. So let's go ahead and do that. Okay. So I could pull a p outside of the whole thing. And then I get the 1 minus p to the k minus 1. Okay. Usually I like to think about this thing as starting with 0, right? And then I have my x to the k, because we start with a constant, then we have x squared, x cubed, and so on and so forth. But if I started with a 1 and I subtract off a 1 up there, then I still start with x to the 0, x to 1, right, so on and so forth. If I start with a 4 and have a k minus 4 up there, it's still going to sum to the same thing, because I still start with a 1, right, x to the 0, which is 1, x to the 1, so on and so forth. Okay. So the fact that I have a 1 here and a -1 here doesn't change that this thing will sum to 1 over 1 minus p. Okay. And I have this p sitting out in front. And then 1 over, see, 1 minus 1 is 0, and then minus a negative p. So this is like a p times 1 over p, which just sums to 1. Which is what I expected, right? If I add up everything from the probability mass function, it should sum up to 1, right? This is everything that could possibly happen. If I add all those things up, it should always sum to 1. So the thing that we're going to want to do, so that's tied in with this thing that we call geometric series. So if we're going ahead and computing an expected value, for instance, right, we don't want to just sum this thing up. We want to sum this thing up if we end up multiplying by k. And so then the question would be, how do I end up getting a, right, since it's tied in, how do I end up getting a k in front of this formula here? That would be the question. Right, I have this. I really want to be able to say something about maybe x to the k, or actually maybe even x to the k plus 1. How do I get from this to this? What's that?
Is it the derivative?
Just the derivative. Yeah, that's just the derivative. Right? That's sort of over and over again. I'll have this formula that tells me what something sums to in some nice, clean, fairly clean way. I don't know, as clean as you want it to call it, right? But fairly clean way, closed form way. And if I take the left-hand side here, I get my k out in front, and then I have my x to the k minus 1, which is sort of what I want. Okay? Which means that I need to take the derivative of the right-hand side also. Not a Calc 1 class, I'll let you remember your quotient rule or your chain rule, right? We can either write that as a 1 minus x to the -1 and take the derivative, or we could use a quotient rule. But either way, when you take the derivative of the right-hand side, you'll get 1 over 1 minus x squared. Okay. So we now have a formula that tells me how to sum these things if I have a k in front of this. So if I'm back here at my expected value, okay, and I plug in x equal to 1 minus p, because that's what's in here. I didn't even have to multiply by x here. Right? Now if I let x equal to 1 minus p, then what do I get over here? It looks like I'll get a 1 over 1 minus p, whole thing squared. And again, 1 minus p, or quantity 1 minus p is p squared. That's a 1 over p squared. Okay. So I can factor this p out, and the rest of this becomes 1 over p squared, and p times 1 over p squared is, p times 1 over p squared is?
1 over p.
1 over p. Oh, we never even talked about, see, we always have to talk about parameters first. How many parameters does a geometric random variable have? Since it's tied to a Bernoulli random variable, right, Bernoulli trials, it has to have a p, but there's nothing else. There's nothing else. It's only one parameter and it's only p. Right? We're not repeating something a fixed number of times until, and counting. We're just repeating it until the failure, but that has nothing to do with another parameter. Okay? So there was just that one parameter, and that one parameter is p. And so I can use that parameter. It says the expected value is 1 over p. Okay. So if the question is, I have these light bulbs and 10% of the time I try one and it doesn't work, that's what I'm going to call success, right? How many light bulbs do I have to test until I get the first non-working light bulb? The answer would be 1 over 0.1, which would be 10. Okay. If I'm going to flip a coin until heads appears, since the probability of success is equal to 1/2, a fair coin is 1/2, then how many times am I going to have to flip a coin until I see that first heads? How many times do I expect? The expected value would be 1 over 1/2, which would be 2. If I'm going to roll a die until the first 6 appears, and so I start rolling, and I count the number of times I have to roll, and then the 6 appears, and probability of success is going to equal 1/6, so the expected value would equal 6, right? I expect to have to roll it 6 times. Sometimes it'll appear on the first time. Sometimes could take 100 rolls before that 6 appears. But on average, I expect it to appear on the 6th time. Right. So let me, a little time here. Let's jump over here to R and just see on that same thing. Jump back over here, right? On that, actually the same R file that I put on the last classes, on the second half of it has some geometric random variables type of questions. And so here's what I'm going to do. Remember D with it, so geom is the geometric random variable. So D geom gives me my probability mass functions. I'm going to pick P equal to 0.6, I'm sorry, 0.1 I guess I have here. P equal to 0.1, so think of the light bulbs, and that's the probability of a failure, I guess. And then I have this, remember if you see two numbers with a colon in between it, it's asking for a vector, and so that would give me the numbers in vector form, 0, 1, 2, all the way up to k, and I let k equal to 100 to start this thing. So this should give me the probability mass function, the values coming out of the probability mass function for a geometric random variable with p equal to 0.1. At least it's giving me the first 100 terms that are coming out of that. And then if I plot those, notice when I plot these things, so I get this graph that looks like this on the bottom right-hand side, but notice I added 1 here, right, to my vectors because I needed to shift. I plugged in 0 to k because R thinks about geometric random variables this way, right? Where it's just counting the failures until the first success. If I want to think about it in the way we're thinking about it, and the book thinks about it, I need to add 1 to it, and then that's the probability mass function for that. Okay. So right? So if I use RGeom, right? Now RGeom is going to take a random sample from a geometric random variable for us. Right? So this is the situation in which I'm pulling. I have all these boxes full of light bulbs, and I want to pull one out and test it, and I want to know how long do I have to pull these out and test it until I find the first non-working one. That's a success for us in this case. Okay. And so I can get a sample of size 1,000, right? I have all of these results here. Okay. Notice, sometimes it's a 0. Of course, that's because that would have been one that was a failure on the first try. I'm sorry, a success, a non-working light bulb on the first try. What's the largest thing that I see? A 35. Oh, there's a 41. Right? There's a bit of a range there. Okay. And if I look at the histogram, oops, I should have added 1 here. Right. If I look at the histogram, right, that's the histogram, and if I plot the probability mass function over the top of it, that's what I end up getting, right? And I can see it fits it pretty well. That's because our probability mass function is also called a frequency function. If I repeat something often enough, it's giving me that picture of how often, right? And I see all those samples, all the histograms I get from my various samples, fit that probability mass function to a reasonable degree. If I want to go down, I know what the expected value is. Let me just jump down here. right? If I do this 100 times and I look at the mean, notice I should be getting values near 10. And I see sometimes they're a little bit below 10, sometimes a little bit above 10, sometimes they skew a little bit, up to 11. I think I saw 12 there earlier. But they're all sort of centered around 10. And if I take a large enough sample size, I expect that number to be very, very, very close to 10. Right? If I were to repeat this experiment, is that 1 million times, right? Then I expect means, right? Average values very close to 10, and notice we're getting things like 9.9987 and 10.001. That's the law of large numbers. I repeat something often enough, and what I expect to happen will happen. Right? Same thing up here. If I take a large enough sample, let's say 1 million, my histogram, this might slow me down a little bit. Oh, you know what, I can't do that on this histogram, but yeah, I'm not going to do it on this histogram. Right? It's giving me an error for a reason. But anyway, if I do something often enough, we'll just say it this way, then my histogram should look exactly like, or almost exactly like, my probability mass function. The only other thing, let's see here, the cumulative distribution function, right, would be that picture of I think I had to put a +1 in here again. See, that's sort of annoying. I have to keep track of my +1s. Ooh. Or not, I don't know. Well, it doesn't matter, I guess. We can see they sort of fit reasonably. I think I'm off by 1. I think it's vertical. But anyway, the idea that what is a cumulative distribution function? It's telling me the step size is the size of my probability mass function. So since my first value was 0.1 and the second value was 0.0, 0.1 and 0.09, the height of the second function is 0.19. It's the sum of those two. Remember, the cumulative distribution function is telling you the probability x is less than or equal to some value. Okay. So we have that. Again, as we start calculating intervals, it's very nice to be able to work with those sorts of things. Okay. And mean, max, min, right, variance. In a case like this, I didn't write down variance. Do we have time for variance? We do have time for variance. Let's go ahead and figure out the variance. The variance in this case is 90. Let me go back over here. Okay. Let's finish off with the variance. If I want to calculate the variance, then I want the expected value of x squared. Okay. And if I want to compute the expected value of x squared, then I want a k squared out in front here, 1 minus p to the k minus 1, and then a p. And then the question would be, how do I get another k out in front of this? Okay. How do I get a second, ultimately right here, how do I get a second k out in front of all of this? Well, how did I get my first k out in front of it? Took a derivative, right? How am I going to get my second k out in front of it? Could be a derivative, except I have a k minus 1 here, so what am I going to have to do?
Multiply by x and then differentiate.
If I multiply by x first, then I can put that x up here, and now if I take the derivative, right, now I'll have my k squared x to the k equal to, and I need to take the derivative on this side. And again, this is not a Calc 1 class. I'll let you guys remember how to take the derivative of a quotient rule there. But let's just point out that when we're doing such things over here, is this my binomial, with the geometric series, right? I have my original geometric series, which is this one up here at the top. And then if I take the derivative of each side, I get this formula here, which helped us with our expected value. We got our 1 over p squared. It's all back here. It's all on Blackboard. You can see it back right. But if I want to, I can start from this point and I can differentiate each side of the equation. Well, after I've multiplied by an x, right, and I get my k squared out in front, and I take the derivative of that, which gives me this formula right here. Okay. So I can get a formula, which is equation or formula 4 on that handout, which is on Blackboard. And then now if we do the same thing as before, what are we doing? We want to plug in 1 minus p in for x. And notice if I plug 1 minus p in for x, I'll get a p cubed in the denominator, and I'll get a 1 plus 1 plus minus p, so I'll get a 2 minus p in the numerator over a p cubed. Over a p cubed. But then we always had this extra p floating around here. So when I have my p cubed times a p, then 1 cancels and I end up with a p squared in the denominator. I'll let you look through this. But we get our formula for our second moment, which is 2 minus p over p squared. Not the last time we're going to go through these calculations like this. We'll do this again. Right. And so then my variance is my second moment minus my expected value squared. So I have this 2 minus p over p squared minus, and then my expected value was 1 over p, so its squared is 1 over p squared. I subtract things off, and notice I get 1 minus p over p squared. Right. So the variance of all of this, and again, it's nice to have a variance formula because I don't have to keep asking the question. I don't have to keep going back and figuring out what's the variance of this thing. It is the probability of a failure divided by the probability of success squared in the denominator, right? Okay. So in our light bulb question, it would be a 0.9, which is the probability of a failure, which is actually a failure is a working light bulb for us. Divided by 0.1 is the non-working light bulb is our success squared, which we expected to be 0.9 over 0.01, which is actually 90. And if we get back to R, we'll notice, you can still see it in this bottom corner here. I got a variance that was very close to 90. That's what I would have expected to happen. So that variance, remember, tells us how much things are spread out. Maybe the more useful calculation later on will be something called, remember, it's called standard deviation, which will be the square root of that 90. The square root of that 90 is, what, 9.2? 9.3 maybe, or something like that. But it's telling us, the average value is 10, but we saw a lot of values from that probably mass function near 1, 2, 3. There are values that are up in the 150s range, but on average I expect them to sort of be spread out about 9-ish from what the mean is. All right, we will stop there. I have quizzes, you can pick them up on your way out. I'll put them over here on this board. That way we don't have people bunching up. Okay. You pick one up on your way out, and we will talk a little bit about geometric, mostly done, but then start talking mostly about negative binomial and hypergeometric.